Hello, 8th grade. Welcome to week 10. We're talking about atomic models. Now, we actually started last week when we talked about Democritus and Dalton and their models of the atom. This week, we're going to be talking about Thomson, Rutherford, and Bohr. And of course, the model of the atom has advanced little by little. Our learning target will be for today to explain how J.J. Thomson advanced the understanding of the atom from J. Dalton's model. You probably know that the wires strung between these high towers carry electricity, but did you know what electricity is? It actually consists of a constant stream of tiny particles called, you guessed it, electrons. Electrons are negatively charged fundamental particles inside atoms. Atoms were discovered around 1800, but almost 100 years went by before electrons were discovered. John Dalton discovered atoms in 1804. He thought they were the smallest particles of matter, which could not be broken down into smaller particles. He envisioned them as solid, hard spheres, that they could not be broken down. It wasn't until 1897 that a scientist named J.J. or Joseph John Thomson discovered that there were smaller particles within the atom. Thomson was born in England and studied at Cambridge University, where he later became a professor. In 1906, he won the Nobel Prize for Physics for his research on how gases could conduct electricity. This research also led to his discovery of the electron. In his research, Thomson passed current through a cathode ray tube, similar to the one seen here. A cathode ray tube is a glass tube from which virtually all the air has been removed. It contains a piece of metal called an electrode at each end. One electrode is negatively charged and known as the cathode. The other electrode is positively charged and known as the anode. When high voltage electric current is applied to the end plates, a cathode ray travels from the cathode to the anode. What is a cathode ray? Well, that's what Thomson wanted to know. Is it just a ray of energy that travels in waves like a ray of light? That was one popular hypothesis at the time. Or was a cathode ray a stream of moving particles? That was the other popular hypothesis. Thomson tested these ideas by placing negative and positive plates along the sides of the cathode ray tube to see how the cathode ray would be affected. The cathode ray appeared to be repelled by the negative plate and attracted by the positive plate. Now I want you to think about what this means. This meant that the ray was negative in charge and that it must consist of particles that have mass. He called these particles corpuscles, but they were later renamed electrons. Thomson also measured the mass of the particles he had identified. He did this by determining how much the cathode rays were bent when he varied the voltage. He found that the mass of the particles was 2,000 times smaller than the mass of the smallest atom, the hydrogen atom. In short, Thomson had discovered the existence of particles smaller than atoms. This disproved Dalton's claim that atoms are the smallest particles of matter. From this discovery, Thomson also inferred that electrons are fundamental particles within atoms. So question, we know that atoms are neutral in electrical charge. How can they be neutral if they contain negatively charged electrons? Take just a moment and pause the video. I want you to think about this question. How can they be neutral, atoms, if they contain negatively charged electrons? Well, atoms also contain positively charged particles that cancel out the negative charge of the electrons. However, these positive particles weren't discovered until a couple of decades after Thomson discovered electrons. Thomson also knew that atoms are neutral in an electrical charge. So he asked the same question: how can atoms contain negative particles and still be neutral? He hypothesized that the rest of the atom must be positively charged in order to cancel out the negative charge of the electrons. Now, nobody really knows for sure. Perhaps Thomson was at a Christmas party with some friends and they knew he was working on this and really wanted an explanation. So he envisioned the atom as being similar to a plum pudding, mostly positive charge, the pudding part, with negative electrons, the plums, scattered throughout it. Another question: how is our modern understanding of atom atomic structure different from Thomson's plum pudding model? Is it different? Take a second and pause the video to think about this question. Well, today we know that all of the positive charge in an atom is concentrated in a tiny central area called the nucleus, with the electrons swirling through empty space around it. The nucleus was discovered just a few years after Thomson discovered the electron, so his plum pudding model was very soon rejected. In summary, in 1897, J.J. Thomson discovered the first subatomic particle, the electron, while researching cathode rays. To explain the neutrality of atoms, Thomson proposed a model of the atom in which negative electrons are scattered throughout a sphere of positive charge. He called his atom the plum pudding model. So, are you able to identify how J.J. Thomson advanced the understanding of the atom from J. Dalton's model? Remember, J. Dalton talked of atoms as being solid spheres and that you could not break them down into smaller parts. If you're still not sure, feel free to go back and check the video one more time. Otherwise, feel free to move on. Welcome back to week 10 of Atomic Models. Today, we're going to see how Ernest Rutherford advanced the understanding of the atom from that of Joseph John Thomson's model. Tom is shooting baskets. He's trying to hit the backboard so the ball will bounce off it and into the basket. If only the backboard was bigger, it would be a lot easier to hit. If the ball misses the backboard, it will just keep going, and Tom will have to run after it. Believe it or not, the research that led to the discovery of the nucleus of the atom was kind of like shooting baskets. In 1804, almost a century before the nucleus was discovered, the English scientist John Dalton, here seen on the left, provided evidence for the existence of the atom. Dalton thought that atoms were small particles of matter, which couldn't be divided into smaller particles. He modeled atoms with solid wooden balls. In 1897, another English scientist named J.J. Thomson discovered the electron. Mr. Thomson is seen here on the right. It was the first subatomic particle to be identified. Because atoms are neutral in electrical charge, Thomson assumed that the atoms must also contain areas of positive charge to cancel out the negativity charged by electrons. He thought that an atom must be like a plum pudding, consisting mostly of positively charged matter with negative electrons scattered throughout it. The nucleus of the atom was discovered next. It was discovered in 1911 by a scientist from New Zealand named Ernest Rutherford. New Zealand is off the east coast of Australia. Through his clever research, Rutherford showed that the positive charge of an atom is confined to a tiny, massive region at the center of the atom, rather than being spread evenly throughout the pudding of the atom, as Thomson had suggested. The way Rutherford discovered the atomic nucleus is a good example of the role of creativity in science. His quest actually began in 1899, when he discovered that some elements give off positively charged particles that can penetrate just about anything. He called these particles alpha particles. We now know them as helium nuclei. Like all good scientists, Rutherford was curious. He wondered how he could use alpha particles to learn about the structure of the atom. He decided to aim a beam of alpha particles at a sheet of very thin gold foil. He chose gold because it can be pounded into sheets that are only 0.00004 centimeters thick. Surrounding the sheet of gold foil, he placed a screen that glowed when alpha particles struck it. It would be used to detect the alpha particles after they passed through the foil. A small slit in the screen allowed the beam of alpha particles to reach the foil from the particle emitter. Now let's think about this experiment just for a minute. What would you expect to happen when the alpha particles strike the gold foil? Keeping in mind, at this time, most people believed that atoms were relatively solid structures, like a plum pudding. Take a second and think about this. What would happen when alpha particles struck the gold foil? Well, the alpha particles would penetrate the gold foil. Alpha particles are positive, so they might be repelled by any areas of positive charge inside the gold atoms. Assuming the plum pudding model of the atom, Rutherford predicted that the areas of positive charge in the gold atoms would deflect or bend the path of all alpha particles as they pass through. You can see what really happened. Most of the alpha particles passed straight through the gold foil, as if it weren't even there. The particles seemed to be passing through empty space. Only a few of the alpha particles were deflected from their straight path, as Rutherford had predicted. Surprisingly, a tiny percentage of the particles bounced back from the foil like a basketball bouncing off a backboard. So what can you infer from these observations? What if you were Rutherford? Or better yet, what if you were standing next to Rutherford? What should you be able to infer from these observations? Why is this happening? Well, you could infer that most of the alpha particles were not repelled by any positive charge. That's what was observed. Whereas a few were repelled by a strong positive charge. Rutherford made the same inferences. He concluded that all of the positive charge and virtually all of the mass of the atom are concentrated in one tiny area, and the rest of the atom is mostly empty space. Rutherford called the area of concentrated positive charge the nucleus. He predicted, and soon discovered, that the nucleus contains positively charged particles, which he named protons. Rutherford also predicted the existence of a neutral nuclear particle called neutrons, but he failed to find them. Nevertheless, his student, James Chadwick, discovered them several years later. Rutherford's discoveries meant that Thomson's plum pudding model was incorrect. Positive charge is not spread evenly through an atom. Instead, it is all concentrated in the tiny nucleus. The rest of the atom is empty space, except for the electrons scattered throughout it. In Rutherford's model of the atom, the electrons move around the massive nucleus like planets orbit the sun. That's why his model is called the planetary model. Rutherford didn't know exactly where or how electrons orbit the nucleus. That research would be undertaken by later scientists, beginning with Niels Bohr in 1913. We'll be talking about him next. New and improved atomic models would also be developed. Nevertheless, Rutherford's model is still often used to represent the atom. So a quick summary. Ernest Rutherford discovered the nucleus of the atom in 1911. He sent a beam of alpha particles toward gold foil and observed the way the particles were deflected by the gold atoms. From his results, he concluded that all of the positive charge and virtually all of the mass of an atom are concentrated in one tiny area called the nucleus, and the rest of the atom is mostly empty space. In Rutherford's planetary model of the atom, the electrons move through empty space around the tiny positive nucleus like planets orbiting the sun. So, are you able to explain how Ernest Rutherford advanced the understanding of the atom from J.J. Thomson's model? If you're still not sure, feel free to go back and review the video one more time. Otherwise, feel free to move forward. Have a great day. 8th graders, welcome back to week 10. We're on atomic models still, and we're going to be talking about Bohr's atomic model. We need to know how Niels Bohr advanced the understanding of the atom from Ernest Rutherford's model. Look at the people in this picture. Do you see how they are standing on different rungs of the ladder? When you stand on a ladder, you can stand on one rung or another, but you can never stand between two rungs. It's empty space. A ladder can be used to model parts of an atom. Do you know how? We'll look at that in just a moment. The existence of the atom was first demonstrated around 1800 by John Dalton. Then, close to a century went by before J.J. Thomson discovered the first subatomic particle, the negatively charged electron. Because atoms are neutral in charge, Thomson thus thought that they must consist of a sphere of positive charge with electrons scattered through it. In 1910, Ernest Rutherford showed that this idea was incorrect. He demonstrated that all of the positive charge of an atom is actually concentrated in a tiny central region called the nucleus. Rutherford surmised that electrons move around the nucleus like planets around the sun. Rutherford's idea of atomic structure was an improvement on Thomson's model, but it wasn't the last word. Rutherford focused on the nucleus and didn't really clarify where the electrons were in the empty space surrounding the nucleus. The next major advance in atomic history occurred in 1913, when the Danish scientist Niels Bohr published a description of a more detailed model of the atom. His model identified more clearly where electrons could be found. Although later scientists would develop more refined atomic models, Bohr's model was basically correct, and much of it is still accepted today. It is also a very useful model because it explains the properties of different elements. Bohr received the 1922 Nobel Prize in Physics for his contribution to our understanding of the structure of the atom. As a young man, Bohr worked in Rutherford's lab in England. Because Rutherford's model was weak on the position of the electrons, Bohr focused on them. He hypothesized that electrons can move around the nucleus only at fixed distances from the nucleus, based on the amount of energy they have. He called these fixed distances energy levels, or electron shells. He thought of them as concentric spheres, with the nucleus at the center of each sphere. In other words, the shells consisted of a sphere within a sphere within a sphere. Furthermore, electrons with less energy would be found at lower energy levels, closer to the nucleus. Those with more energy would be found at higher energy levels, farther away from the nucleus. Bohr also hypothesized that if an electron absorbed just the right amount of energy, it would jump to the next higher energy level. Conversely, if it lost the same amount of energy, it would jump back to its original energy level. However, an electron could never exist between two energy levels. So, how is an atom like a ladder? Think about that for a moment. How is an atom like a ladder? Well, energy levels in an atom are just like the rungs of a ladder. Just as you can stand only on the rungs and not in between them, electrons can orbit the nucleus only at fixed distances from the nucleus and not in between them. Bohr's model of the atom is actually a combination of two different ideas: Rutherford's atomic model of electrons orbiting the nucleus, and German scientist Max Planck's idea of quantum, which Planck published in 1901. A quantum, or quanta for more than one, is the minimum amount of energy that can be absorbed or released by matter. It is a discrete or distinct amount of energy. If energy were water and you wanted to add it to matter in the form of a drinking glass, you couldn't simply pour the water continuously into the glass. Instead, you could add it only in small fixed quantities, for example, by the teaspoonful. Bohr reasoned that if electrons can absorb or lose only fixed quantities of energy, then they must vary in their energy by these fixed amounts. Thus, they can occupy only fixed energy levels around the nucleus that correspond to the quantum increases in energy. Quick question. The idea that energy is transferred only in discrete units, or quanta, was revolutionary when Max Planck first proposed it in 1901. In other words, no one had ever thought of that before. However, scientists already knew about matter. What scientists already knew about matter may have made it easier for them to accept the idea of energy quanta. Can you explain why? How could they accept this idea of energy quanta based on what they knew about matter? This one's a little trickier question, isn't it? Take a moment and think about it. Go ahead and pause the video for a moment. I'll be right here when you come back. Hey, welcome back. Scientists already knew that matter exists in discrete units called atoms. This idea had been demonstrated by John Dalton around 1800. Knowing this may have made it easier for scientists to accept the idea that energy exists in discrete units as well, quanta. Summary. In Bohr's atomic model, electrons move around the nucleus only at fixed distances from the nucleus based on the amount of energy they have. The fixed distances where electrons may orbit are called energy levels. Bohr arrived at his model by applying Planck's idea of energy quanta to Rutherford's atomic model of electrons orbiting the nucleus. So, our big question, did we reach our learning target? Are we now able to explain how Niels Bohr advanced the understanding of the atom from Ernest Rutherford's model? If not, you may want to go back to the video, take a few notes, and see if you can put those pieces together so you can see the whole puzzle. If you're okay with this piece, feel free to move on.